Hello, this is a tree of my Haskell garden, and it grows level by level. Let's consider how this Haskell program works. What we built here. Oh my god, this is madness. No, this is Sparta, this is Haskell. Okay, let's start. So, first of all, I have some helper functions here. The first is print the tree, to print it in a nice way, as you see at the start of this video. And replace env function, which take a list and produce a new list where we replace one of the elements given by index. And we give an index of the element in the list and the element of the list and the list, and produce a new list. The new element on this index is set. So the next thing is parent direction, which means that when they have nodes and when every node has a parent node, and we need to know from which direction from the parent node we go to this node, either the left, either the right. And the parent index, I will talk about this later. This is just integer. So what is the main idea of the algorithm? How can we do this? It's based on level order traversal. I made video about this, you can see the link below. This level order traversal is based on breadth search algorithm, and it uses a list as a queue. So we take our tree, put it into the list, and begin to build a new list of nodes, and they go from the root node to the deep to our tree by the levels. And at some point we will find a node which has either the empty left tree, either the empty right tree. And this means that they found the node on the minimal level where we can put our new node. And this is the whole main idea. Then we take this algorithm, this level traverse algorithm, and begin to deconstruct our tree. The level order builds a sequence of nodes, but we will create a sequence of trees. What I mean sequence of trees? Okay, as the first tree, we have a tree which starts from the node of our initial tree, and this is the first tree. When we take the left branch and right branch, this is also trees, and we cut them all, and we have only the root node without left and right, and it start from the start of the list. Then we put the left and right sub-branch from the right of the list, and so on. When we take our left sub-branch, cut this each left and right subtrees, and put it again to the right, and for right, and so on. So this means that they step by step reconstruct our tree, and at some point we will find this node which either have empty left or empty right sub-branch, and at this point we need to stop this reconstruction. We will have a list of these reconstructed trees, and then we need to fold this list again we need to, when define the node, the node where we can put our new element, we put it there, and we have this list, and we need to fold this list again to the total tree. Okay, this is the intuition, but let's start to write this, and you will understand, I think, what I mean by what I mean here. Okay, I will start from ins function. It will this function will produce this list of reconstructed trees, and it takes some I parameter, which means which represents the index of the current node which we reconstructing in our tree. Of course, we start from the root node, and it always in the left of our list, and this means that we start from the E0. So let's this is a type signature. We have some int which represent the position in our list of the tree, and then we have some a. This is the type of the tree, elements of the tree, the type of the element which we want to insert. And when we need some list which contain our initial tree, which we will reconstruct. So this list is represented via triples. The first element as triple is parent direction. Parent direction. Second is parent index, and third element is tree itself, binary tree itself. So we start from this, and in the end we will get exactly the same type. This function will return exactly the same type, but did reconstruction of our tree, and we need then to fold it. So let's start from some simple case, then the inserting with some index e, current index e, some type A, inserting some new node. We want to create a new node, and this is its type, and we have an empty list. In this case we will return an empty list. If we have not the empty list, we will unpattern match it. So let's unpattern match this tail with access, and here we have a triple which we need to unpattern match. So I will call it PD, PE, parent direction, parent index in this list, and the second thing is tree itself, but I will start from looking at empty tree. So if we have this case, this means that I need to create a tuple. I need to create a tuple with no parent, no matter the index of the root, because there is no parent. I just put 0 here. It will actually not used. And then I need to create a node containing this, our insertion A, and empty branch from the left and from the right. So when this means that then we have a list which contain an empty tree. We can't reconstruct empty tree. Actually, we need to create a new tree to replace our empty tree with a new tree, which constructed with node, which contain only one this inserted value and the empty left and right subtrees. And I do this here. Okay. The next thing I need to do is to pattern match some other cases. If I insert in some A, and we also have some not empty list, but it now contains some node here. Let's put this into parentheses. And this node contain, of course, some value, and we need to find the case then one of the branches are empty. They search for this, and I will catch it here. If we have left empty, I pattern match it here, and we have some right subtree. Okay, so if we catch this case, in this case, what we need to do? Okay, this means that I already find the position. It has we go. I tell that we go in a level order traversal, and we found first minimal level where we have a node which contain empty left subtree, and we can use this empty space to put a new value, our A value, inside this space. This means that we need our XS, which actually is used as Q. We need to take our XS and put a new triple to it, and this triple contains this node, actually a new node which constructed from this node, this value, this right some branch, but we need to replace this empty with our inserted A. And of course this is easy to do. We need to create a triple. We need to put use this PD and PE from this node. Its direction from the parent same, and its parent index same, and we need to construct a new node here. Node with value V, and left some branch must be not empty, it must be A, and we will use A here for construction, and use right sub-branch from the right, because it's not empty here. And I think that's all, I think. No. Here I can't, of course, I can't use a here. I need to build a node. I need to build a node with this a, because then I have the type mismatch. So I need to build a node with the a and with two empty subtrees. So actually I put a leaf. This is a leaf. I put it here to the left branch for this node. And this, I think, should work. Yes, this should work. Okay. And now let's look at symmetric case. Then we have right some branch empty. Let's look at it. It's absolutely symmetric. I use empty. Here we have left subtree, and here we have empty right branch. And in this case, I need to use left here, and as a right, I need to create a leaf with this node constructor. And this will give me what I have expected. Okay. But what if we have to insert some other case? Then we have no empty left or right. This means that we need to continue our level working on the tree here, and we will use a recursion for this. Okay, how we can use it? First of all, we need to use this triple as a head of the list. We need to use exactly same triple as the head of the list. But we reconstructing our tree. This means that I must to remove L and R from here and replace this with the empty constructor, because we will take this left and R, which I replace here with the empty constructor, and put it to the end of our list, of our stack, of our queue. So we take our triple, and our triple is the first element of the list, and the tail of the list is built via our insertion. This means that we need to call our ins here, but we need to increment our index I in the list, because we go to the second element. The first element we return here, and here we construct a second element, and this means that I need to increment the index of the list. And of course I need to pass a here, value itself, and then I need to take our tail and add to our tail the concatenated with the list which contain left and right sub-branch, I think. yes, left and right some branch, and left and right some branch represent via triples, of course. The left have, and they need to show the direction here. For left it has direction left with our parent index I, and left subtree. Okay, and for right it have direction right, parent index I, and the position I is the position in the list for which we deconstructing our tree, and the right tree. Okay. Okay. And this is correct. I think this should work. This should work. Let's try to compile this function and look how can it work. Okay, I will load our Go file, and it compiles. It's good. Look at our type signature. Okay, we can see that our signature, and let's run it starting from the 0 index of the list, starting from the first element, and for example I want to add some S node here, and I need to provide a list which contain my tree, and I will use this tree tier, which have a root A and tier, and from the left tier from the right. From the left we have B, D and E, and from the right we have C, E, F and G. So okay, I will print this tree to print it our tier. Okay, we have a tree of this type, and now I will use our ins function. I will start from 0. I want to put S here, and I want to reconstruct a tree, our tier tree. So I need to wrap it into the list to continue our construction. And let's call this. Okay, some problems. Of course, I need to use not tree itself. I need to use a triple here with parent direction, and parent, and parent index. We have no parent. This means that I just put 0 here, no matter. And in this way, and parent, I need to capitalize this letter. And here you can see that I construct a deconstruction list of the tree. So okay, let's look at our tree again. We have this tree and how it reconstructed. Okay, look here at the first element we have a root of this tree. The root of this tree is contain a value, and we remove left and right subtrees, and you can see empty here. This means that its left and right subtrees are go to the right of the list. We can see this node B here. Of course, we've reconstructed left and right subtrees it mark that it have direct direction left, which means that we go from A to left here, and node C here, which have also direction, which has direction to right, which means that we go to the right from A, and we have this index 0, which shows the index in this list of a parent. Parent is A, and parent is first element of the list. This means that the index is 0. And then we have a reconstruction of all the tree to the end. First of all, we reconstruct our B, which means that our B is reconstructed to this E and to E, and so where is that F here? Why there is an A here? Okay, I think I make a little mistake. It changed somehow the construction order, but this mistake I think doesn't have any it hasn't any influence on final result, but let's okay, then we unpattern match these two cases. Then we have something empty from the left or from the right. We doesn't. This means that we are found our node, and we doesn't need to pass it to the end. We need to pass it to the first, to the position as it found. This means that we stop our searching for a vacant place, empty place. So let's reload. Let's insert again, run our print here again, and now look here. We have A, B, then C, then we have D as expected, and this D is not reconstructed. It has some S here, as you can see, and then we have E as expected, and then F and G as expected reconstruction. And after that they need to write a function which will merge this list, merge it, and so build a new final tree from it. How can I do this? Okay, let's start to write our merging function. I need some helper. I will call it insert. It takes some node to insert and some tree, and at first it call our ins actually with initial 0 with our A, and create this triple. Okay, we have no parent and 0 and our tree. So we have this structure, this list, which shown here. It's shown here. Okay. What to do next? How we merge this? How we merge this? We merge this starting from the end of the list. So we take the last element, found its parent, found its parent in the list. This element contains the index of the parent in the list. It has also direction, and we need to remove this last element and put it into the parent. So we need to change the place there, the parent, with a new parent, and we need to put this last node to the left or the right branch of the new parent. So this mean that we need to somehow fold. I will call this function fold fold our list, and let's define our fold. I will start from type signature. Actually, our fold take this type, our list of triples, and produce a list of triples. Actually, produce a list of only one triple, because it folds all the triples to one triple. And now let's start from definition. If our fold called with a list containing only one element, then we return only one element. But if our fold has some not empty list with more than one element, this means that we need to, first of all, we need to merge our last element of the list and sorry, I didn't need to put much here. We have some data, our list of data. I need to take the last element of the list and merge it with the init of the list. Init is all the lists cut it. If we cut the last element from the list, the init is the state part of it. So, and we merge the last and the init, and then we merge this, we will receive a list again, and we need to fold it again. So we use a recursion here. Hence, and I think this is our folding function definition. But of course we need to define a merge function. And let's start from our, I didn't do the type signature here. I didn't want to do this. So let's how we call it. In the merge we use as a first argument, we need a triple. As you see, we use last of our list. So this is last triple we used. Actually this. And we unpattern match it here. We have some direction, some parent index, and we have a tree. Okay, we have a part of the tree, some subtree, and we merge this with a list. Okay, I will call it access. So how the merging done? Actually, merging is replacing of our list. and we have a replace nth function for this. I talk about this in the start of the video. It's just to replace some element of the list, and let's use it here. Let's look at type signature. Okay, we need to use our parent index here to replace the parent, and new value. We need to use some new node here to replace our parent, and I call this node just node, new node. And the next thing, we need to use our XS. Okay, and of course we need to define the node. How to define a node? To define a node, we need to, first of all, we need to know the direction to which we need to pass our tree, and we do this using the case pd off. And if we have direction left, we will create some node from the left. If we have direction right, we will create some node from the right. And if we have no parent, this means that nothing to do. We need to stay the list as it is. A node as it is. And to stay the node as it is, we need to just pick up this node from our list with our parent index. Actually, we change the element with itself. So, but if we have to put to the left some branch, we should create a new, I will call this function which we create new node L, and for creating a new node we need to pass a old node, and old node we can give it with this expression. Okay, and same way for a right branch. Okay, and let's define our new node L, and new node L. Here we take an old node which we need to on pattern match with our PDPA, and we need to reconstruct and pattern match our node itself. This is have some value A, some nomad word from the left, and some right subbranch. Nomad from the left because we will replace this thing with our T, and actually there is an empty branch there, and we need to create a new triple at first with our PDPE and our new node. With our new node with A, T and R, I think so. Yes, A, T and R. And exactly the same thing for a right branch. We have L here, no matter, from the right, and put left and right here. I think this should work. I think. Let's try to compile this. No parent, not in scope, no parent, and parent. How define our end parent? I need to capitalize here. Reload. Variable note in scope. Of course, I need to use T here. And reload. Not in scope and parent. Parent unit. I need to capitalize here. And it compiles, yes. And now moment of the truth. Let's try to merge our list. And after doing this, we need to produce a final tree. So to run this, I need to write insert function. Insert function with our new node S, which we want to insert, and our tree tr. Let's run this. And to understand what we got, we need first of all write our print tr. We have this tree, and do the insertion, and then we modify it, and of course I have a triple here. And first of all, I need to extract this triple, the third element of this triple. And to extract it, I need the helper function, which I call get third. So it's take a tuple and pattern match it and return third element. So if I run this, reload and run this with our get third, what's happening? Get third. Why it doesn't work? Okay. Of course, I need that first to take. Let's look at its type. It have a list. So first I need to take first element of the list. First element of the list. This is first thing. And then I need to extract. And now I extract this tree. Okay. And now let's print it. Print this. Print it, this tree. Yes. As you can see, we inserted the S as expected. So the tree was like that, and we add the S to it, to the next level as expected. So let's try to add some more elements to our tree. Some more elements. So for example, I need to save this function, I think. Thanks. And I will call it as insert. It takes some tree and a and do this thing and produce a new tree. A here, T here, and now I can call this as insert T and S here. So now I need to have a list. First of all, I need to have a list of some nodes to insert, and I will use the numbers for it, infinitely many numbers. No, infinitely many can be too many. I will use 11. Then I have mapped this using show. This will give me this thing, and then I need to use. I want to fold this list with our sinsert function. Let's look at type signature fold, type signature of insert. So I can use them together. I can compose them. Fold as insert initial battery. I need initial battery, and I will use an empty battery. Pams. And I will use this thing here. This thing. I think it will produce me a new tree. How do you think? Let's try to run. Pams. I built a tree. I can print it. Yes, at 11 elements. 11 elements. All elements are inserted line by line, as you can see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If you want 12, you can change this to 12, and 12 goes here. If you want 12, 30. 30, I think. No matter. Okay. Okay. Level by level, you can see. Inserted level by level. I'm not lying. Yes. Okay. But okay, let's see this for a moment. And I want to check some degenerate case. Then we have some tree which constructed, which degenerates to list. Will our function work correctly on this case? Let's check this. We have some trx with a node which go to the left. Right is empty, but the left is a node. With the right is empty, but the left. Okay, one A, B, B, and this again node, again C, and now it's empty. Okay, and now it's empty. Let's load our Trx. Trx. Yes, this is a degenerate tree. Let's check how our function will fill the levels of this tree. Yes, yes, you can see. Yes, it fills this level to fill them all. And in the end, let's do some animation from which started this video. How to do animation. Then they have growing tree, infinitely many, level by level. How can they do this? How can they do this? First of all, actually we have something for this. We can use this foldl as insert empty. But here I will use not foldl, I will use scanl, which is like foldl, but it will produce a list of trees, all intermediate trees which we get, and I want to print every this tree. Okay, look at its type signature. Scanl. Yes, you can see that here we have a list of battery of strings. And now, and now, having this binary tree of strings, I need to print every tree with the delay. So I need to insert, print, delay, insert, print, delay. And look at our print tt function. You can see that this is a monadic function which takes some battery of showable A and produce an IO action. And here I have a list of binary trees. So I need to take this list. And fmap. I think I need to fmap this total expression, total list with some lambda function which takes a tree. At first it print this tree, as I said, it's print and see, and then it do the free delay. delay for many microseconds or nanoseconds, I don't know. Okay, print tree, print delay, and this will work, I think. Yes, it produces me a list of IO actions, and to transform this to action, I need to use a sequence function. Sequence underscore, because I don't need these results, and I need to do this. So thanks, and you can see we have this visualization. Tree is grows level by level, but we need to have infinitely many trees, and let's build them. Let's Haskell build them while I drink some tea. Yes, it works. I think it will work. I can go to sleep now. So guys, this was a level order insertion into the tree, but this is, I think this is effective implementation, because we doesn't why we use this list, because we doesn't need to reconstruct all our tree, to traverse all our tree to find this final point. We need only to find the first node with empty branch, and then to construct it again. This means that what does this mean? What I want to say? This means that we have some sorry. This means that we have saved some time to traverse all the nodes. But in this implementation, they use this replace end function at int, not fast, I think. And in the next video, I want to replace this implementation of the list using some hash map or some maybe tree of Haskell to speed up this replacement at first. And I think this will be faster. So guys, thanks for watching. Push like, push subscribe. See you in the next video, and bye bye.